Okay, so hello everyone again. So today we are going to talk about the structures that we can use to define or to describe the cyber-physical systems. If you remember from the previous sessions, the tool we are going to use is Papyrus. And also Jennifer mentioned a couple of weeks ago, a couple of lessons before, that in SysML we have different diagrams. And for us, based on conceptual modeling, that is the things we are going to do today, are two main diagrams, block definition diagrams and internal block diagrams. Today, because we only have 2 hours, we are mainly focused on block definition diagrams and how to structure your model and how really can use this kind of diagrams to represent your cyber-physical systems. So the topic for today is modeling system structure. Okay, what is the meaning of modeling a structure in the scope of cyber-physical systems? For us, we are mainly focused on the system structure. That means to define the terms that compose your cyber-physical systems and also its hierarchy or their hierarchy and their relationships. So for us, from the structure perspective, we are only focused or we are only interested in blocks, so that components as a black boxes. The next day, we'll go inside, go deep into each component to describe their internal structure. But this is part of another diagram. So the modeling structure for cyber-physical systems, as I mentioned, is based on blocks. And there are 2 different kinds of diagrams. The first is the block definition diagrams, that, as I mentioned before, for us blocks are like black boxes, and internal block diagrams, where blocks are like white boxes, so we can analyze what is happening inside, and we can know how the components are related to one each other. So, as I mentioned, the elements that we use in the block definition diagrams are those that are needed to define the system. And in the other diagrams, we only show how these components are used. So today, we would like to work only with these components. This is an example of things that we are going to prepare today. This is a BDD, a block definition diagrams. Well, as you can see in the screen, we have the system structure. This is the system we are building. And in this diagram, we said that the system is composed by different blocks. And at the same time, we also have some components that are also based or composed by also different components. So this is the kind of information that we are going to represent in these block definition diagrams. And the next day, so these are the name of the package, the name of the diagram. We also have here the header, the diagram KIME, the kind of document we are building here. We are describing a package and the diagram name. In Papyrus, we are not going to use this representation because we are opening a diagram. So the name of the diagram is the name of the file you are using. And in Papyrus, we are going to use only to work only with this internal part of the diagram. So this is the components of the diagram. And in the case of internal block diagrams, we have the same header, identifying here that this is an internal block diagram with the name of the block we are analyzing and also the components inside. So for the next day, we will be focused on identification of these internal relationships and also the internal ports that represent the component. So in this kind of diagrams, we also have blocks, relationships, and finally, ports. Okay, so this is the topic for the next lecture. And to drive both sessions, today and the next Wednesday, we are going to build an example. And this example is called Swimming Pool Control System Case Study. Which are the main elements? If we are talking about swimming pool, of course we have a nice swimming pool here. And we have to fill this swimming pool with water, and the water is stored in a reservoir. Of course, there is some city pipes to move the water from here to our swimming pool. But in our case study, we are only interested on the control of a water pump to move water from the reservoir to our internal swimming pool. This water pump, as I mentioned, move water from one side to another, to one part to another place. And this water pump is controlled by a controller. And also, we would like to get some information about the swimming pool so that we have an information panel for the swimming pool. So this is the example, the case study we are going to use today and the next Wednesday. So let's start today with the block definition diagrams. The first, why model blocks? Why we need to model the CPS, the cyber-physical systems, in terms of blocks. What do you think? Cyber-physical systems are complex systems. That means they are composed by complex and different elements. And this kind of definition or this kind of diagrams let us the possibility to represent a domain model. That means all the diagrams we are going to use are specifically defined to model a system using some specific concepts. So when we are building and we are modeling these kind of diagrams, we use specific names based on the domain of the domain specific we are building. So that for today and for our case study, the terms we are going to use are, for example, swimming pool, of course, pumps, water maybe. So we are modeling the components and the concepts that take part or that will be involved in our diagram. So this box, as mentioned, defines the glossary of things in the problem space. And we need to move from the problem space to the problem solution. And the diagram is the way we are moving from one scope to the other. These block definition diagrams graphically depicts how these things are related. In the previous slide, we saw the swimming pool, we also saw the pump, and in this kind of diagrams, we are going to visualize to represent graphically these connections. In terms of systems engineering, this kind of diagrams depicts the static structure of the system, things that never change when we are representing the system. Because for things that can change, we have some of the diagrams, activity diagrams, state machines, and so on. So this is the static part of the system. And identifies, of course, what are the elements or what the system consists of. And finally, why we use this kind of diagrams? Because based on that representation, we have a common language to communicate users, stakeholders, and the engineers that we deploy or we develop these kind of systems. which are the elements we are going to use today and the next day, and next Wednesday. At least we have 6, 7 components: blocks, value types, rating blocks, actors, constraint blocks, comments, and ports. So the next slides will explain all these concepts in deep. So what are blocks? And this is something that I mentioned before. Blocks are the main structure that we're going to use. So for us, it's a modular unit. That means all the things we're going to use here are blocks. So it's very simple. It's like classes in UML diagrams. So these kind of diagrams are based on UML class diagrams, but with some constraints, with some significant changes in terms of how relationships are managed, which possibilities or will reduce capabilities in relation with the UML diagrams. These have a subset of the UML classes. For us, a block describes only a part of the system. So we are focused on analyze which and how many instances we have of each block. And the powerful of blocks for us is that we can represent different concepts, so that we can model using blocks a pump, but also we can use a block to model water. Water are different than pumps. So we use the same representation for represent or for analyze or for describe all the elements of our system. So for us, a block is a description of all the instances that had the same or more or less the same characteristics. So for us, a block is like a class. That means when we model a block, we need to identify properties, operations, and relationships. But the name we are going to use is different because we are modeling different elements. As I mentioned, a block can define logical or conceptual entity, physical entity, or some hardware and software components. And when we need to define a block, if we consider that this part of the system could be reusable in different parts, we can use it. If they are not reusable, we can put this part like properties. So when we would like to reuse this kind of information, or at least they have their own behavior, we need or we must to define a block. So in object-oriented programming, the term applied to elements inside a class is property name. For us, the term is not property, but feature, because these represent a characteristic of the component or the element. So that when we are defining a block, there are 3 different kinds of features. Some of them are structural features that define the internal structure and properties. And here we also have 4 different kinds of features. One is called parts. The second is reference. The third is values. And the last, but not the least, are ports. In terms of behavioral features, we use this kind of features to show or to model how each block is interacting with the other part of the systems. So we define how this component, this block, interacts with the environment or with some other blocks, and also how they modify the state of the block. That means in terms of behavioral features, we can define operations and receptions. Both are more or less the same than functions or methods in object-oriented programming. The idea, more or less, behind operation is like they are methods, like void methods. Yes, and receptions are more or less functions that are returning values, more or less. It's not really the same because methods are inputs and so receptions are inputs and operations are interfaces we have outside. And also we can define some constraints. Constraints are specific limitations or specific rules that we add to the block. For example, what happens if you have some values or some properties or some features that always should be positive values? We can create a constraint and say, this specific feature will only accept positive values, non-negative values. So you can write your constraints when you are building this. So you can define and you can identify this kind of constraints. Some recommendations when you have to identify and create this kind of diagrams. First, of course, identify blocks. That's right. And for each block, identify its structural features. The next, identify its behavior. Then later, you decide about some modifiers. For example, some features could be read-only, or could be static, or some other modifiers we are going to present later. And this is a very interesting thing. Let me go back to some previous slides. Oh, sorry. If you see this diagram, it's something that I don't like to show. Because if you see this diagram, you are showing at least the root level, because this is the system we are building. At the first level, we have these components, and in the same diagram, we are presenting at second level, because we are decomposing this element and explaining and presenting the elements that the mount assembly is composed by. So when you define this kind of diagrams, it's better if you only present one level instead of displaying everything in the same diagram. That means we try to represent only concepts that have the same level of abstraction. And how to represent this composition? Creating a new one where the mount assembly is the root and then the other components. So in terms of clarity, it's better to have only elements with the same level of detail. Is it clear? So it doesn't matter if you have 1, 2, or 3, or 20 diagrams, because it's better to isolate these compositions and only have at the same level components with the same level of abstraction. Do you understand my English? Yes? Okay, so the next, as I mentioned before, only use the BDD to represent system structure, something that I mentioned maybe 20 times in the last 15 minutes. And use IBD only to represent internal compositions and their relationships. Something that we will explain the next day. When you describe this kind of relationships and when you identify the things that flow across these relationships, you have to assure that connectors, when you connect one block with another block, that connectors are compatible. It's something clear in computers. If you have a mouse with a USB and you try to connect this USB in a PS2 connector, it doesn't work. So you need to assure that all connectors, all the elements through a connection are compatible. Or something more or less complex, but the next day we are going to talk about. Consider that you have a port that is an output port. It should be connected to an input port, so to an input, or an input, an import. But if you connect two output ports together, never going to work. It doesn't work because both are putting, maybe it's a collision, because both are using the same connector to put things. I don't know if the thing is water or is power, energy, or I don't know. Maybe some electrons moving from one part to another. And another interesting thing, why are we using, or why are we modeling systems? I mentioned before that we are defining the same language. We are writing a domain-specific language, so that all the terms we need to use should be defined. For example, if you are measuring, for example, size, what is the unit you are going to use for size? Maybe meters, maybe centimeters. So you need to define what is a meter for you. So first, identify the kind of measures you are going to use and the things you are measuring. For example, if you would like to measure the volume of the swimming pool, it's preferable to define or to describe a type for volume, because you are managing a concept, not only a value. If I said, this is 1,000, what is the meaning of that? 1,000. Maybe it's 1,000 units of volume. So that is very important to identify at the beginning the kind of types you need to use. Organize your diagrams in packages so that you can model things inside packages. And finally, for those blocks with hierarchical relationships, please model it using generalization and so on. And finally, identify flows directions. When you are moving things, for example, in the case study, we're moving water from the reservoir to the swimming pool, not from the swimming pool to the reservoir. So identify the direction of these flows and which kind of things are flowing through our connections. Something that we have to do in advance when we are modeling our system. So that, which are the main blocks of our system? It's clear. If you remember, based on this general overview of the system, we need to define a swimming pool to represent this concept. We need to create a block for the reservoir to model this for the concept. We also need a block to model the water pump, and the same for the water pump controller, and the same for the swimming pool. And what about water? It should be a block or not? What do you think? Are we managing water from here to here? Yes. So that for us, as water could have some specific behavior, we need to represent water like a block. So please identify all the things that you are modeling in your system. Okay, so the first, if you remember the recommendations of the previous slide, is identify blocks. Is it clear? In principle, we have, for this example, we have these blocks. And the next is, which are the main properties of each block? For example, the features for a swimming pool could be with large depth, 1 level, to know how many water is inside, which is the level of water of your swimming pool. For the reservoir, maybe it's for us in our case study, it's enough if we know only the capacity. And the unit for capacity will be volumes. And the unit for all these features will be meters. And for the water pump, maybe it's the power pumping, the pumping power in terms of volume by unit time. 1,000 liters by hour or so on. Because depending on this power, pumping power, we need more or less time to fill the swimming pool. And for the water pump controller, maybe the features here are not very clear. We need to think more about. But in principle, we can set up these properties. For example, we need to know what is if the water pump is switched on or switched off, is working or not. So maybe we can have a status, and a status could have only one of these three different values. So this is something like a numeric type. What status only could receive are on, off, or pause. And maybe operations for the water pump could be a start, pause, resume, or stop. Maybe. We are not analyzing in detail all the features and all the operations for these components. Maybe for the swimming pool panel, we only can display information on the water level. And for water, maybe it could be interesting in the density, or maybe if you have salt water or any other kind of water. So maybe this could be the main features for our case study. And finally, what's the other thing we need to do to start working with the BDD diagram? Which kind of information requires and provides each block? For the swimming pool, if we have the swimming pool and we would like to control the swimming pool, which kind of information we would like to have or to get from the swimming pool? For example, the water level. But the swimming pool, to fill the swimming pool, we need to put inside water. So swimming pool requires water, and it provides the water level. For the reservoir could be the same. It provides water. We can consider that our reservoir never ends. So we have water and water without any limit. And maybe for the water pump, it provides water. Maybe it requires water from the reservoir, and we provide water to the swimming pool. And the pumping power maybe only provides the status for the pumping power, and the same for the controller. And for the swimming pool, maybe a status of the swimming pool panel is switch on or switch off, is working or not. And maybe the water level to display this information. And finally, so how these parts are related? Swimming pool, of course, is a part of the system. A reservoir is also a part of the system. A water pump is also a part of the system. Pumping power is also a part of the system. Water pump controller is also a part of the system. And the swimming pool panel is also part of the system. I missed to write here in the controller that it's also connected with the pumping power, because the controller is controlling this part of the system. And the water is also part of the system, but it's connected with the reservoir, because water flows from the reservoir, and water is also flowing to the swimming pool. So that using the same structure that we presented at the beginning, we have here our system. It's a block, the whole system, and we also have several subsystems here. And as all these elements are part of the system, we're going to use a specific kind of relationship. That is a composite association, something that we are going to talk in a couple of minutes, or maybe in 10 minutes. So the representation could be something like this. So this diamond, black diamond, means system is a composite. There is a composite association from the system with the other elements. But it's different that the relationship that is, of course, water is here. But it's different the relationship between water and the reservoir, or maybe the water and the swimming pool. So we have two different kinds. Later we are going to explain that we have more than one kind of relationship. So at the same level, we have many different connections, many different relationships. So let's do it with papyrus. Okay, so first of all, how are we going to represent blocks? It's very simple. We have this metaphor. This is the profile identification. That means this is a block. For each kind of component, we have a different label. This is the name of the block. This is the place where we present all the attributes. Later, we are going to explain what should be here, and some operations, and of course, some other compartments presenting the other kind of properties, the other kind of features we have. If you remember, when we talk about the structure, we said we have parts, references, we also have ports, and we have value types. So we have different compartments to represent all these elements. Blocks extend capabilities of UML classes. Why? Because in UML, you only have two compartments, attributes and operations. Here we need more compartments to represent the different kind of features we have. Okay. How are we going to model blocks? Something that I mentioned before. Properties that are the elements or the features of the block. A property has its own type that defines the characteristic, and we have three different properties, three different categories. Value properties, that means a property is a specific value, is a specific feature that represents a quantifiable characteristic. As I mentioned before, for example, height, deep, large, width. These are value properties because they represent an atomic weight. These properties could be represented at non-distributed values, for example, weight, 1,000 kilograms, speed or velocity, 100 kilometers per hour, or maybe you can use some distributed values. This is a uniform, or you have different probability distributions to model the behavior of this property. Maybe we can also have some ranges. For example, tire pressure should be, the minimum value could be 28 and maximum could be 32. And in terms of value properties, sometimes the value is a derived value. That means the value is calculated in terms of some other values. In that case, we have to check, we have to apply a modifier explaining that it is a derived value. The third or second property is power properties. This power property describes the composition relationship. So when you say this property or this feature is a part, it means it is referencing a block. So this part of the system, the control system that we are building here, has a part, has a specific block that is a complex structure. So that part properties describe the decomposition of a block into its constituent elements. So it's something that you can start translating from here to your lab assignment. At the first level, at the higher, at the context level of the lab assignment you are building, you have different blocks. For each constituent, you have a block. Last Wednesday, you made your presentation presenting how many different constituents do you have. So at the context level, you have to create a DVD containing each constituent as a block. And later, you only need to analyze or to go deep in one of the components. For example, if you add as a block, for example, police is a block. You don't know what is happening inside. You only need to know the interfaces you have to the police. So if you make a phone call, maybe this should be an interface where you can represent that there's a phone call flowing from here to here. So we identify the elements, the ports, that means the interfaces that this constituent have, and which kind of information is flowing from one side to the other side. Okay, so our properties describe the components, the constituents of your system. And finally, reference properties. What is a reference property? How familiar are you with object-oriented programming? More or less? High, strong, or medium? Medium, high. Okay, so power properties represent that this element is part of the system. But sometimes you have a reference to an element that is not specifically part of you. Remember, we mentioned here water. Water has a relationship with, for example, pump, or maybe for reservoir, or maybe to swimming pool. Maybe you only need to display that there is a relationship between water and the reservoir, for example. Or maybe it's clearer for you, the pump and the pump controller. The pump internally doesn't have any controller. You are adding a component outside that is controlling the system. So this kind of relationship that is not part of, but I am using that, or I need this kind of information, is what we call reference properties. That means are properties whose values refers to parts of other blocks. It's more clear, maybe the main argument or the main way to know if a feature or if a property is part or is a reference could be something like that. If I remove the system, for example, if I remove the pump controller will disappear or not. If not, that means there is a reference relationship. But if I remove the system, I'm removing all the components. That means all of these are parts of the system. So it's the first way to find the difference between power properties and reference properties. Uh, so let me present these concepts and then later move to Papyrus, because it's funny for you to start doing things with Papyrus and start modeling things. So, if you remember, one of the main types of properties was value types. Value types for us are the definition of components, of the elements of your block. And normally, value types defines a type of quantity. Like I mentioned before, volume, or maybe kilograms, or maybe meters, and so on. So value types can be used in many places. So we define the value types in one place. Maybe it's a very good strategy to have a specific package for these kind of types, to put it inside. All the types should be in the same package, and later we can import it. And when we are defining value types, of course, we can create generalization trees. We can have like classification of different kind of types. And there are three different kinds of value types. The first is primitive types. For example, you can define a kilogram. It's only a name. That's right. It's enough. In SysML, you have 4 different value types, 4 different primitive value types defined. String, Boolean, integer, and real. They are predefined in SysML. So primitive types, it has no internal structure. It doesn't know, they are not owned of any other, like they don't have any other properties. You have a, it's not a block, it's a square, and it's enough. It's the name of the primitive type. The second kind of value types is enumerated. Enumerated is a list of literals. If you remember in one of the previous slides, we said a status could be an enumeration, on, off, false. So we can define this specific enumeration for this value type. That means this specific property belongs to this type. And the last are structure types. Structure types are something like records or assets, something that has some additional properties. So the structure types has an internal structure composed or defined by their own properties. For example, we can create a structure type to represent, for example, size or 3D size. We have 3 dimensions, so we can create a 3D type based on width, in our case could be deep, and large. And we define this specific type. Why we need to write this or to define this kind of concepts? Because maybe later it could be interesting for us to describe that the behavior is that. And we have or maybe there is an agreement in the scope of the project to use this kind of names. And when you say this is a 3D type, all of you knows that this 3D type is composed by 3 different values, where the first is the width, the second is the depth, and so on. So you are putting a common name in agreement with the other people involved in the project. In that case, in the modeling of your system. What happens when you are defining this kind of structure types? There are 2 specific properties from SysML. The first is quantity kind, and the second is unit of measure. Both are trying to represent some semantic in the type definition. For example, you can define a kilogram like a complex type. And the important thing when you are defining a structured type is that you are explaining, or you are adding semantic information, explaining that kilogram is a quantity kind to represent mass, and the unit will be kilogram. So the idea when you define this kind of structured types is to represent the property, the physical property you are representing, and the unit, the reference scale you are using. So these are semantic to your representation. That means you can define kilograms in that way. But you can also define kilograms in that way. Which representation provides more information about the magnitude you are measuring? The first is the primitive type or the structured type. Which is the second one, has more semantic or is more meaningful for the project. So it's up to you. You can define your primitive types in that way, or you can use it like value types that are data types. Okay, so I think it's enough. We can start now modeling our system. So let me sit and open Papyrus and create a new project. And in the new project, we are going to build a new block definition diagram. Is there any question? Not now. Okay. As I mentioned at the beginning of the lecture, I am recording this session, so later, maybe during the weekend, I can put a link to a YouTube site to see the video. So, let's start creating the project. So, new Papyrus project. So the name of the project could be today, maybe the name will be Swimming Full Control System. We are going to model a block definition diagram. At the beginning, we only need to describe or to define this kind of diagrams, but if you have in mind to model more than one diagram, you can select all of them, and automatically Papyrus creates some diagrams to model the other type of components you are going, or the other things you are building. And there is a predefined library with some quantity kind definitions and with some units definitions. So if you want to use it, please check the model with QODB library. It's based on an ISO 8000. It's a subset of predefined measures, unit measures, and quantity kinds. But for today, we are going to use our own quantity types. Okay, now you have the Papyrus dashboard. So it's clear for you. Maybe with Jennifer, a couple of weeks ago, you start working with Papyrus also, with different kind of diagrams, with requirement diagrams, and also with package diagrams, and so on. Maybe. Yes, no? Okay, so do you know the dashboard, the different parts we have here? In the upper left, we have the Project Explorer with all the components, with all the elements of different projects we have. Just behind the Model Explorer. In the Model Explorer, you have all the diagrams, blocks, and components that you have defined inside. This is the place in the center. You have the drawing area. You can drag and drop components inside or blocks depending on the concept you're building. At the bottom of the screen, you have the properties folder, references, documentation, and model validation. At model validation folder, you will get some error messages that you have when try to validate the diagram you are creating. So it's very simple to start creating the diagram. So select the blocks. Let me resize the system. Sorry, the screen. So first, we are going to add the system. That means we are selecting block, drag and drop, and here we have the block. So what is the name of our system? Maybe it could be swimming pool system or swimming pool control will be the name. So once you add a block, in the properties folder, you have the different categories about some SysML properties and some, as I mentioned before, SysML is derived from UML. So we have some internal properties for SysML and some additional properties for UML. So we have the name, swimming pool control. In these days, I will explain some of these modifiers for the block, so don't worry about it now. So we have first. Are you familiar with Papyrus? No. Oh, it's hard. It's very hard to work with Papyrus. It's a powerful tool, but it's very hard. So, first of all, how many containers do you see here? You only see two. One, attributes and operators. You are seeing these both because they are derived from UML. It's like attributes and operations from UML. But we mentioned at the beginning, we have more. We need a part compartment. We also need a container for references, of phone ports, and so on. So you can adapt the containers you can display. So it's very simple. Please put your mouse on over the container or over the block. Press the right button. Go to the filters option and select show high compartments. Control F5 is the same. And here appears all the compartments we have that we can display. Attributes, we will only show here the types the value types. Later we can select which kind of elements we are going to display on each part. Operations for methods, nested classifier, decoration nodes, it doesn't matter now. Flow ports, something that we need to explain the information that is flowing in or flowing out of a block. Constraints, parts, to represent the part properties. Proxy port and full ports, they are different elements. Flow ports are deprecated, so I don't recommend you to use this kind of ports. In all our examples, we only will use proxy ports and full ports, because these are deprecated in SysML 1.3. Of course, references, flow properties, parameters, symbols, and blocks. So, for us and for the goals we have with these BDD diagrams, we would like to show parts, references, at least for today, this both, constraint not for the moment. And we also have another column to decide if you would like to display the compartment name. If you don't check this check button, the name doesn't appear. So if you remember the presentation, when you create a block, you can see only attributes and operations because both were checked. So if you would like to add the name for parts, references, please check that field. When is recommended to check or not the field? If you have more than one compartment that is showing information, is displaying information, I prefer to check the name to understand which kind of information is composing or is displaying in the compartment. So I will check the part, the references, and we can also propagate this selection for all the elements at the same time. The problem is, how many blocks do we have here? No, only one. So propagate, it has no sense. Okay, so for me it's enough, and we have all these parts. So when you are using Papyrus, it's different to select the name and the number of compartments we are going to show than the information that is displayed on each compartment. So we have to do in two different steps. First, identify the compartments we are going to show, and second, the information that we are going to display. Because as our diagrams could be huge, with so many different kind of types and connections and so on, maybe sometimes in the scope of a specific diagram, we don't need to have visible all the properties, all the features, so we can select which part of the block we would like to display. Is it clear? Okay, so how can we select? It's very simple again. Right bottom, filters, show high contents. Here, now for the moment we don't have any specific property, so this option or all these categories are empty, so there is nothing to present. Okay, so we have this swimming pool, that's right. So the next we can add another block to represent the swimming pool. And now the swimming pool, we said at the beginning, we have three different properties. We have three different features: the large, the width, and the depth. So we can create these properties. It's very simple. So if you left the mouse over the block, there is a menu, a contextual menu here to create operations and properties and so on. So I'm going to add a property. Sorry. Add a property. Now for the property, in this element is all the things we are putting inside of a diagram. Papyrus consider that they are blocks, so always the name will be block. Don't worry about it. It's only a name, so change the name. There are some modifiers that later I will explain about that. The visibility of the property. Visible means all the blocks will have access to this property, and there are different modifiers, different levels. Visible, public, private, protected. Multiplicity means how many instances of this field we are going to have. For example, for size, for the length of our swimming pool, how many lengths the swimming pool will have? Only one. But in some other cases, you can have more than one value of this type. Maybe it could be something like a ride or a set of things. So you can decide here the multiplicity. Aggregation is something that will have more sense for all the kind of properties, and the type, default value, and something that we will talk maybe next day about subsetting and redefined properties. So let me define here the first, length. Okay, now still length is undefined. Maybe you can say, okay, length is a real number. So you can update the type and you can select, okay, for me, this is a real number, so that I can select one of the primitive types and select real. Okay, it's enough.
How have you entered that part?
Okay, I selected the properties folder, and when I move to the type option, press in the three dots, and here when you have the menu open, you unfold the primitive types, and then I selected data type real. Is it clear? Okay, but what about the thing I mentioned before? What is the meaning of length and real? Which physical measure, with physical property are we measuring here? Maybe it has more sense if instead of using a real number, we said length is size, or maybe it's a meter, or it's a and a specific name. So the next that we're going to do now is to create a specific type for this magnitude. Is it clear? Okay. So how are we going to do this? If you remember, I said the best practice is to have all these concepts in a specific package, so that we are going to, in the Model Explorer, we are going to add a package for these units, okay, for these internal types. Is it clear? No?
I cannot see the Model Explorer.
The Model Explorer?
You have maybe.
Maybe some of you, I don't know why, you have some problems, some of you, because when you start, you open your Eclipse environment, the Papyrus profile is not active. It's not active. So you can have to change the perspective. And as in any other Eclipse application, go here to select the Papyrus. In my application, as I download specifically version of Papyrus, the Papyrus is set up as default. So that's why maybe if you try to open a project and you have a problem with the folder names or maybe with the Model Explorer, it's because it's the Papyrus profile, the Papyrus view is not, or perspective is not active. So in the Model Explorer, we are going to add a new package, so press the right button, new child, package. New child package. And the name of the package will be own types, for example. Own types. We have just defined a package. You can select your own name. The idea inside is to explicitly describe that all types will be there. I don't know if I can present maybe the appearance preferences. Okay, so I try to increase the fonts for the menus, but I don't exactly remember how to do it. Do you know how to do it in Eclipse? To increase, maybe it's in window preferences or window appearance. No, preferences. About model editor. No. Okay. For the next day, I will increase the fonts. So, once we have created the package, now it's time to create a new diagram to include this kind of blocks. So, over the own types package, we are creating a new diagram, and again, it's a block definition diagram. And the block definition diagrams will be types. So we have just created the package. Inside we have just created a new diagram, new block definition diagrams. And now we have an empty diagram. Okay, so here is where we are going to add these types. So please let me show you again the thing we start working at the beginning of the lecture. So we have status for on, off, pause, and we also have a new that will be meters. Okay? So let me show you how to do in the 3 different ways. One primitive type for kilograms, or for meters, for example. One enumerate for status. One data type, a complex structure type for example, density. Okay? So, let's start with the primitive type. It's very simple. In the types, again, over the diagram, press the right button, on the own types, package, new child, primitive type. What's the name? For us is meters. And that's all. We have just created a new primitive type in our model. But it is not visible in our diagram. What's happened? I have just created inside the own types package, I have just created a new primitive type. How I did it? I press the right button over the own types. A new menu, submenu is open, new child, and at the bottom there is a primitive type. Okay, so it is visible, but it's not still in the diagram. So to make visible this element is very simple. Press, drag and drop over the diagram. Okay, so now we have a new type. And for us, this type has a semantic. Maybe for us it's enough. So let's move again to the previous diagram, the block definition diagram for our system. And now we can say the length is not a real number, but this is a meter. So we can change. And from the conceptual point of view, I don't mind how are you representing meters. If you are using a float, a double value, or real, I don't mind. Because for me, the conceptual type is meter. And it's enough. It's clear? That's why we always recommend to define your own types, because you are representing magnitudes, not using specific types for languages or for UML or for some specific languages. Okay, so do the same for the other fields with large depth, length. I can change for using large. So let me add a new property with it is also meters. Oh, I made a mistake with the name. It's meter. Sorry. And next, depth meters. And finally, water level meters. Okay, so now we have this swimming pool block defined. The next maybe is to create the water pump controller. So please do it by yourself. You have a couple of minutes to do it. And here we have a problem, because we said that the status is an enumerated type. So how are we going to do it? Yes, in the block, let me show you a second way to create elements. If you can see, the block palette has some operations, and somehow it has some shortcuts. So there is enumeration, so you can drag from here. But in which diagram are we going to create the enumeration? Not in the block definition diagram, but in the types. So please change to the other diagram. Oh, sorry. Change to the types diagram, blocks, unfold and select the enumeration. And for us, enumeration is status. And the way to create the values for the enumeration is to press the plus button here and add literals. In this enumeration, you have the name, if abstract or not. In our case, it is not an abstract type, so it's a public type also. And here you can write your own literals. In the case if you would like to relate this specific type with some use cases in the old diagram you create with Jennifer, you can press here. But as we don't have this kind of use cases, we cannot link both definitions. So for us, it's enough to create some literals, and for us will be on, off, and pause. So name is on, it's enough. Off is enough, and pause it's enough. Okay, so as you can see in the diagram, we have a problem because I have just defined the type here, but I can't see the specific values. How can you present the values for this type? 1 minute to do it. 50 seconds. 40. 30 seconds. Please do it. Don't forget, right button, filters, compartments. And then so as I mentioned before, every time you want to present or you want to show something, it is a two-steps procedure. The first is to open or visualize the compartment, and the second step is to visualize values. That means right button, filters, show on high compartments. For me, I would like to only show the literal compartment, and the next filters, hide contents, and to show literals. Okay, that's right. Now it's time to specify the type for the status. So I can select in the on types the status type. Okay, it's fine. It's very simple. Don't forget forget, move to the block definition diagram, select the water pump controller, check or click on the status attribute, and then finally select the type. So it's the same than before. Okay. So the third is to create the volume unit. Okay, so how do you like, or how do you prefer to represent volume? For example, cubic meters. This could be the name. That means our type will be M3 cubic meters. This magnitude is representing volume, and the unit, this is the quantity kind, and the unit will be cube. That's right. So this is the thing we are going to do now. Instead of creating a primitive type, we are going to create a value type, writing this semantic or increasing the semantic for it. So again, move to the types diagram. Again, open the blocks palette. There is a value type. So drag and drop value type. Write the name M3. And as you can see, as this block is a specific, is a stereotype by value type, we have two attributes: quantity kind and unit. So let's create these elements. So the quantity kind, we don't have any, so that status, oops, sorry, status value type here, quantity kind. So let me create a new one here. Oops, sorry, 1 minute. Unit, I don't have anyone. Oops, a UML, sorry, add the UML. Value type M3 UML M3. Oh, oops, I don't know why it doesn't work now. Okay, so we have to create our own quantity kind. So first of all, new child, sorry, is new child quantity kind, because we still don't have any quantity kind, so it is a new type of block. We have just created a new one, and for us is volume. Okay, now once we have created the volume, we can assign for the cubic meters for the quantity kind. Now we have, oops.
How did you create it? Yes, I can find the child with the label.
You don't have that child.
I think.
Right button, new child on the SysML child.
Ah.
So it is a SysML child, quantity kind, volume. Oops. Okay. And now again, we can do the same in own types. We have to create a new child for units. The name for unit will be M3. And for the M3, it is a unit. It is very important now, because don't forget that at this level, each unit we are creating should have a quantity kind property assigned. Because for us, M3 is a unit for volume, so we have to link both components. That means once you have created your M3, we have to assign the quantity kind. Let me show you what happened if we don't assign any quantity kind for the unit. If we validate the model, Papyrus said the required feature quantity kind must be set for M3. So the way to do it is quantity kind. We are going to change the property, and the quantity kind we edit, and now the quantity kind, the type is, and the instance is, sorry, the name for the quantity kind is for us. So let me select, sorry, the name is sorry, I have to change this type quantity kind, and the instance is from is volume. Okay, so it should work now. Oops, it doesn't work. Oops, quantity kind, quantity default value, quantity kind is type is sorry, oops, editing. I don't know what is happening. Oops, editing here. Oops, this is an instance, nothing. Oops, instance enumeration. Oops. Oops. Quantity field. List. Oops. So I don't remember how to change it. So for the next day, I will explain you how to do it. Oops. Oops. I have it. Quantity kind. Feature and the value. It is a string literal. Okay. I don't know why the first time it doesn't work. So I select the quantity type. I press the plus button to add elements. I have just added the literal string here. So I wrote volume. Sorry, I didn't wrote nothing here, and in the value field I wrote volume, and that's all. Okay, so the next is to assign again to the unit. For us, the unit is M3, and we have just created our value type. In quantity kind, we have put a link to the quantity kind we created here, sorry, this. And from unit field, we added this name is the unit. Estás en el volume, en el 3 para mirar, ¿no? Sí, este es el 3, que este es el que hemos creado. Este en el 3 es la unidad, este es el punto. Lo voy a borrar y lo voy a borrar.
Ajá. Eso es ahí. Yo no vuelvo. Ah, tú lo pusiste ahí.
Okay, so now we have.
I can't find the volume.
Yes, but the way here, close the door, please remove your here, press here, then, okay, yes, but it's the first one. And now here, select this, remove it, remove with the cross, red cross, and now add string literal, string, literal string, sorry, literal string here, and now write the name, all name is empty, I need to fill, and then only value, write volume. Okay, now you can select the value, now you can validate this. Okay.
And the link that volume has with M3, did
Yes,
do it or?
yes, Papyrus do it.
Oh.
Okay, so now uh, the next, the last thing for today, we still have 10 minutes. The last thing for today is to create a water pump. So we add a new block, water pump, with one field, one feature, and is pumping power. Oh, sorry. Instead of I prefer to create reservoir instead of water pump, because water pump the unit is different, it's volume by hour. So let me change the name instead of water pump, reservoir, and the name is volume is capacity. The name of the property is capacity. The type for us is M3. Okay. So now we have 3 different blocks. So let me switch to the slides. We have just created the types. And now let me explain you how to create these part properties so that you can do it during this weekend. I will work in the same project, so for the next Wednesday I will provide you a new version with whole components, with all the elements, to continue working all the same with the same project. But from here, from today till next Wednesday, you can do some practices with this project, but also you can start working with your lab assignment to create the blocks for the different constituents, and then to explode and to decompose the main controller for your system, identifying the main components, the main blocks comprising that block. So that properties, part properties, as I mentioned before, they describe composition relationships. It's something that we need because our system is composed by pumps, pump controllers, reservoirs, and so on. So the way to do it is, once we associate both blocks, we have a part property. This type of this is a hierarchical composition. That means the upper part is composed by the related blocks. This composition, or this part property, has 2 different values for multiplicity. Lower bound, so the minimum amount of blocks of this type that the system has. So, how many reservoirs do we have? Maybe one, but maybe we can have more than one. So we can select the upper bound. In the case you select the lower bound like 0, that means during the whole life of this block, you can remove some parts. For example, in our case, could we remove reservoirs? Maybe not. Could we remove swimming pools? Yes, or maybe not. But maybe we can remove the swimming pool panel, control panel, for example, we can remove. So in that case, in the case of this part, could be available or not. We can remove it. The lower bound could be 0. So it's something like optional part of the block. How we model this association, as I mentioned before, is a composite association. That means we have one block, we have the second block, and we would like to describe, or we would like to do that this block will be part of this. So we create a composite association from here to here. And what happens when you add this composite association? Okay, don't forget, in UML, the arrow notation specifies that in this kind of associations, the ends are always navigable, and the class owned the association ends are navigable, but the part that is owning the composition is not navigable. So it's more easy than explaining. It's easier if you see what the things I mentioned now. So in Papyrus, when we add the composite association, we can see in the properties description all this information, the name, one member end, and the second member ends. And if you see the diagram, the part end with the navigable, that is navigable, that means with the arrow, should be owned by classifier. That means this part of relationship will add here a property with that name. So the arrow from block, in that case satellite, to altitude, attitude, and orbit control. In this end, we have to add a name. This name will be the name of the property here, and it should be owned by classifier. And in the other part, don't forget to write here composite, because the relationship between this block and that is composite. And in the other part, in the whole part of the composition, the composite end, aggregation is known, because this is not aggregated with this. The name should be empty, and the owner will be association. So once we have that, once we have done that, in the part section, in the part compartment, we can see here the name of the end and the type. So let me do it in Papyrus. So I would like to say that, or to represent that the swimming pool is a part of the swimming pool controller, sorry, swimming pool control. So that we select here, if you press, can you see here it's very small. Can you see here a small arrow? It's very small, it's very tiny. So when you press here, you can select all the different association types you have. So please select part association. When you select part association, mark the whole part of the system and then move to the second part of the system and then drop on the other class, on the other block. By default, Papyrus create the connection, the relationship between the whole part of the relationship and the end part of the relationship. Writing names in both parts, writing multiplicity in both parts, and writing a name here. By default, Papyrus is working in that sense, in that way. But what happened? Don't forget the thing that I have seen in the previous slide. What happened if I try to validate the model now? Papyrus said, okay, there is a problem in the relationship. All these problems are derived because here we have a name and also we have a name here, and because of the values that Papyrus has assigned by default to each specific part of the relationship. So that sometimes the message is quite complex. So let me solve all these problems. So we move to the properties, select the relationship, and try to do the same that in the previous slide. For example, if you remember the member end, the right part, at the beginning we left the swimming pool control blank, empty. Here we left the name. We changed the owner from association to classifier, and that's all. Oops. So let me remove the name here. Let me change the ownership to classifier, and that's all. Validate the model. Oops. There is also another problem, is the aggregation attribute to the property must be composite. Sorry, I forgot in some place to write composite. Here is composite. Where is the problem here? Maybe we have a different problem here. Oops. Maybe the problem is in this. Oops. Aggregation here is composite because we are referring to a type, a value type that is something like a block. So that's why we had the problem. Validate. Okay, that's right. Normally, in this kind of compositions, we don't need to write any name here because the semantic of the composite association is enough. So we can remove this name because maybe the name could be, this is part of this. So, but this is the semantic of the association. That's why we can remove the name. And now it's clearer than before. We can use the semantic of the diagram. So we can move here, and also we can move here, and we can move here. We can change the position from here to here, and also we can change the look and feel. And now it's clearer than before. Okay, but what's happening here? I haven't seen the name of the part. So, how to solve it? Do you remember how to do it? It's very simple. Select the swimming pool controller, the swimming pool control block. Move to filters, show high contents, and now we have a part here with the name. Okay, now it's clear. You have a part property with the name swimming pool that is a type of block swimming pool. So it has to do the same. So for the next, you can do the same for all the blocks to have all the parts in the swimming pool. Any questions? Now it's clear? So as you can see, Papyrus is not very friendly because but it's a powerful tool because it's following the standard step by step. So sometimes when you try to do something and Papyrus said it is not possible, please go to the standard, to the XML standard, and read the restrictions or read the information about the error, because sometimes the problem is that you are trying to do things that the standard doesn't allow. Okay, so do you like it, the lecture today?
Yes.
Yes? Okay, so don't forget next Wednesday we can continue here, because maybe for the next Wednesday the other rooms are not available yet, so we can continue. Okay, in this moment I will stop